Any questions? Any questions? Lab today, Wednesday's group checking out. No lab. You got my email. Group lab report due Friday by 5 p.m. Friday's lab will be doing the VIDIC and checking out on Friday. Test on Friday. That cannot be moved. Any questions about anything? We're going to have the white handout. We got the purple. We're looking at the aldol reaction. Aldol reaction, a alpha carbon enolate attacks a carbonyl, makes an aldol. The aldol will usually dehydrate to make an alpha beta unsaturated carbonyl compound. Basically, the aldol reaction makes a new alkene. VIDIC makes an alkene. This reaction makes an alkene. We did a symmetrical aldol. There's your alkene we made. It's also an alpha beta unsaturated carbonyl compound. We made the alkene. Of the alkene, the two carbons, what were they originally? This was the enolate carbon there. And what was this carbon originally? Those are the originals. That was a carbonyl, that was the enolate. How do you know that was the enolate? Because it's next to a carbonyl. The other carbon was originally a carbonyl. Okay, that was a symmetrical aldol, just basically this molecule reacting with itself. Hydroxide catalyst, that's where we left off. Let's start here. Can you have two different molecules? For example, this could be the enolate carbon, and that could be the carbonyl. And if this reacted here, which of those products would you get? That reacted there, which would you get? A, B, C, or D? C. So I said C? C? How would you get there? How would you get that if these two reacted? What do you have in an aldol reaction? An enolate and a carbonyl. You would get B. Here's your enolate. And here's your original carbonyl. The original carbonyl is gone. If you do mechanism, I know no way in the world that you would get that right there from reacting these two. Mechanism, this attacks here. This carbon attacks here. Hopefully you've done this. How do you get the others? How would you get this molecule? If you break this apart, break it apart, it goes back to what? It goes back to enolate and carbonyl. Enolate, that becomes carbonyl, so you have carbonyl, boom, boom. Enolate carbonyl. That's what you started with. How would you get this? How do you get this molecule? Break it apart, you get enolate, and the other becomes carbonyl. What do you have? Same molecule. That's where this reacts with itself. You get the A. How do you get this compound? And now I have to apologize to you because I knew now see how you would get this. How do you get this? Tell me again, who's that? Enolate here. Enolate there. And that attacks here. So that's the enolate, and this is the carbonyl. Break this apart into enolate plus carbonyl this attacks here, you end up losing, you make aldol, you lose water to make the double bond. Yeah, that reacts with this to get that. How do you make this one? Enolate attacks itself, that's the aldehyde. I mean, if you turn that into carbonyl, that's the same aldehyde as up there. In the end, if you combine these, this can act as enolate or carbonyl, this can act as enolate or carbonyl, you get 4 possible products. Not going to be a good reaction. Up there, you only get 1 product. There's only 1 enolate that can be formed, and there's only 1 carbonyl that can be attacked. Down here, you have 2 enolates that can be formed, either that one or that one. And then you have 2 different carbonyls, so it's 2 times 2. To do a mixed aldol, you have to have a reason for selectivity. Here's a reason over here. If you do this reaction, you just get 1 product. Why do you only get 1 product? Or why do you not get 4? Well, where are you going to make, you got base, where are you going to make enolate? That's the only place you can make it. That is not acidic, that is not an alpha CH. You're only going to make enolate right there. There's only 1 enolate possible. So that's going to cut the number of possible products from 4 to 2. Now this could react with itself and get the first reaction we showed. What else could it react with? We could draw itself here. Will it prefer to react with the aldehyde or with the ketone itself? Which is more electrophilic, aldehyde or ketone? Aldehyde, because here we have a donating group. Aldehyde is more reactive. Now we could have made that argument on the previous one, but this reaction actually works. And if we take this and do our mechanism, we can eventually get to that product. Now imagine that many of you are sitting here, how do you get that product? Well, we did the mechanism last time and you should have been looking at it in the interim time. Okay, there's the product. That reaction is pretty good. That's actually called a chalcone. That's irrelevant information. Very commonly made type of compound. It's an alpha-beta unsaturated carbonyl. That's what aldehydes give. We made an alkene. That's what an aldol gives. This is the second way we've seen to make alpha-beta unsaturated carbonyls. What was the first way we saw? The first way we saw was back over here, where we halogenated and then we removed HCl to put in the double bond. Okay? And when we eliminated by E2, we made alpha-beta unsaturated ketone there. With this method, we do not build a larger molecule. I mean, we added no more carbons than what we started with, put the double bond in. Over here, when we made the alpha-beta unsaturated carbonyl, we made it from 2 larger molecules, and so we're building up something bigger And so it's a more versatile reaction of building larger molecules. By the way, the recall is right there. Another way to make that product is to start with this alpha halogenate. We know how to alpha halogenate, and then do an E2. But again, you have to start with the entire molecule already built, essentially. Up there, we can build a larger molecule. Okay, you can also do aldols intramolecular, where you come together and make a ring. If you take this diketone, treat it with sodium hydroxide, it will do an intramolecular aldol and lose water. What size ring will we make? Why 6? Jason, did you say 6? Why 6? What's going to do what?
The outside bond's going to attack the carbonyl.
Make enolate here?
Yes.
Or there, it's the same thing. And this can attack what?
Carbonyl.
Attack over there. What size ring are we making? Let's do this. That's going to give, let's see, I've got, in between the carbonyls, I've got 3 carbons. 1, 2, 3. Then the carbonyl. So that's carbonyl, and the carbonyl has a methyl. So that was carbonyl, but this attacked carbonyl. Electrons up or onto the oxygen, so we got that, where we just made that bond. This attacked carbonyl. That attacked carbonyl, electrons onto the oxygen. So what size ring did we make? That's a 6-membered ring. And then in our mechanism, what happens next? This picks up an H back from water. Then what do? We form enolate again. Then anytime we can make a pipeline, kick off a leaving group, we do that. And we end up with what? A 6-membered ring with double bond here and a methyl there. So there we go. That's a product we can make. If we go backwards, we can break these apart into enolate and carbonyl. Which carbon, top or bottom, is the enolate carbon? Top, the one next to the carbonyl. That's your enolate. So we can break this down into this enolate carbon. And this carbon down here was originally what? What's the other component of the aldol reaction? Enolate and carbonyl. So we can break that down into carbonyl. And if we break it down, we get back what we started with. When you see these alpha beta unsaturated carbonyls, enolate carbon attack the carbonyl, but then it lost water by putting in the double bond. That's why the O is now gone from there, which used to be the carbonyl. So this is an example of an intramolecular aldol. It's the same old mechanism. Could we have gotten another ring here? First of all, what if that attacked here? Same exact product. Could we have made an enolate somewhere else? What about here? Could we have made that enolate? Yes. What if that attacked here? What size ring do we get? Show that product if that happened right there. What would the product look like? Show the aldol product arising from that right there. Now again, when I say aldol, that right there is actually strictly an aldol because it's got the alcohol. But for me, I would usually say dehydrate them always and show the dehydrated aldol product. Some dehydrate spontaneously, some don't. What I'm looking for here is the dehydrated aldol product. We do it stepwise. Do it mechanistically. What does that product look like? If that attacked here, if it did a nucleophilic addition, we'd first get this. This would pick up a proton. There's the original aldol, where enolate attacked carbonyl, this picked up. Now if we dehydrate it, where's the double bond going to be put in? Well, how do you dehydrate? What's the first step of the dehydration here? Make the enolate. Where are you going to make the enolate at? Right there? No, next to carbonyl. Right there. And when you make that from the base, what does it do now? It expels the hydroxy group to put in the double bond. So if you think mechanistically, you just work your way there. What size ring is this? 4. Double bond here. What's here? Methyl. There you go. You see? So, I mean, either enolate it's favored, but which way is it going to cyclize? We're going to get the 6-membered ring or the 4? 6. You're going to get the 6, because 5 and 6 are your favored rings. Because for this thing to attack, it ain't going to like having to bend over that much. So it's going to be very slow to do it. Even if it did, you can just kick that enolate back off. All this is in equilibrium. It's going to gravitate towards this way, my 6-membered ring. What size rings are favored? 5 and 6. What about a 7? Is that going to be better than a 5 or 6? No. Bond angles get too wide. 5 and 6 are your best rings when you have choices. Where do we see, over here on Vioxx? Right here. What's going on here? It's an aldol. Instead of hydroxide, they use triflaminous base. It's a weaker base, but it can be used. If we break this alpha-beta unsaturated ketone down and go backwards, which carbon, top or bottom, was the original enolate carbon? Top, the one next to carbonyl. The bottom was originally what? The carbonyl. Those are the two components, enolate and carbonyl. So if we break that down, phenyl, just make it a plain enolate. And here's the ring with the SO2, etc., SO2 methyl. And that carbon was originally what? Carbonyl. Well, that's that over there. It's just drawn flipped around, but it's SO2 phenyl ketone CH2O, CH2O, O bonded to carbonyl, CH2 phenyl. That's it. And how did we get this product? Triethylamine took an H, made enolate, enolate attacked carbonyl, just like over here. Ended up making what size ring? 1, 2, 3, 4, 5. 5 made that 5-member ring. After that, OH it was here, was expelled, put in the double bond. That's just a good old-fashioned intramolecular aldol using triethylamine. Make Vioxx, $1 billion drug. Used to be until got cool. Okay, I've already kind of taken us through some going backwards. Show the starting materials for making these. You guys on the left over here, show the two starting materials to make this by an aldol reaction. You guys on the right, show the starting material to make this. Aldol reaction, enolate attacks carbonyl. Enolate and carbonyl are your two components. Okay, when we get through here, we need to move to the Michael reaction, Michael addition. That'll be our last main reaction. Okay, make this here. We get right there plus what? These two with some base. Triethylamine or sodium hydroxide? Yeah? How do we do? Aldehyde, right? There's an H there. When you make that a carbonyl, that's an aldehyde. Those two would react to give that. How do we do it, Sarah? Why would this guy, why would you make enolate there and not over here? Do you have any rationale for why? More acidic. It's between the two withdrawing groups. The withdrawing group doesn't have to be another carbonyl. The nitrile. That's one of those W activated methylines. Going to preferentially make there. This one over here, intramolecular. Here, and right here is what originally? Carbonyl. Treated with base, make anion here, attack carbonyl, you give bond with an OH eventually, and then you make another enolate. Next to this carbonyl, that's why you're able to make enolates here. Kick off the OH, you put in the double bond. Put in the double bond. This carbonyl remains. Enolate, carbonyl. How are we doing with these guys? Aldol reaction, very versatile. One of the top 10 reactions in organic chemistry. How many times have I said that? At least 15. Okay. Michael reaction. We're going to skip the Claisen. We did a Claisen on the quiz. The Claisen is just where an enolate attacks not an outright ketone, but a what? On the quiz, what did the enolate attack? Mark? Well, it did attack itself because it was a symmetrical Claisen. But what is itself? What did it attack? When an enolate attacks a what? Chris? We don't have the quiz? Okay, Michael reaction. Number 3. Conjugate addition, Michael addition. To what type of compound? Alpha beta unsaturated carbonyl. Have we ever made such? Yes. 2 ways we made it. We just reviewed the 2 ways. Those compounds, here's one right here. These are very reactive themselves once we make them. Nucleophiles can add to them. Let's review this. We have this compound. How could a nucleophile add? Well, a nucleophile could add to the carbonyl, electrons up. Give this. Nucleophile add, electrons up. We've been doing that for 6 weeks, 2 months. That's called a direct addition to the carbonyl. We've been doing direct additions for 2 months now. Okay? Just haven't called them direct. They're also known as 1,2 additions. Why? Because if the nucleophile adds, I could do it on either one. If the nucleophile adds here, where does the charge end up? The charge ends up right here. So if that's 1, what's the next number? 2. So it's a 1,2. We'll see what 1,4 means and we'll have a better understanding. We add here, the charge ends up there. Then from there, you can maybe add an H+ source and end up with an alcohol, or if this is an ester, you can reform carbonyl and kick off the leaving group. Basically, that's nothing new. It's called a direct addition. With these type compounds, you can also do a 1,4 addition, which is called a Michael addition, or a conjugate addition. And here, the nucleophile doesn't add directly to carbonyl, but instead adds here. And the electrons move here. Now let's look at this. What does this give? Nucleophile added here, electrons move here, so what's here now? A lone pair. Now what do we call such? A lone pair carbanion next to carbonyl. Enolate. This addition gives an enolate. Does this have any stability? Yes. Look back at the first page. This is why, okay? Does this have a resonance structure? Yes. And electrons here, electrons up, and get a resonance structure of the enolate. After the nucleophilic addition, that would look like what? Double bond, electrons up. This, and this really looks like the enolate because it's the enol with a minus, so we call it enolate. But often you just call that the enolate. But it's, okay, which is the major resonance structure, top or bottom? Bottom, because minus is on oxygen. Why did you say top?
No, I was thinking more reactive.
Well, these always react on carbon,
Yeah.
at least in this class. There are special cases when oxygen might react. For example, when it may be making a 6-membered ring, where if that reacted it was 4. Okay, this is major, so let's look at this here. major structure. So the nucleophile added there, we'll call that 1. Where did the charge end up? Not there, that's 2. Not there, that's 3. Where did it end up? 4. Most of the charge is there. That's why it's called a 1,4 addition. Where here, nucleophile added 1 and the charge was 2. It's also called a conjugate addition because the double bond is conjugated with the carbonyl. You would never do this. Okay, I'm not going to say that yet. A while back, we said whenever you add a nucleophile to a pi bond, remember organic 1, it was usually electrophiles reacting with pi bonds. Pi bond acting as a nucleophile. Here the pi bond's an electrophile. We're adding something to the pi bond. We said you never do that unless the resulting charge can end up where? On a heteroatom. For example, when you add a nucleophile to this pi bond, where's the charge end up? Heteroatom. If you go to aromatic substitutions, and you have to do NAS, it doesn't work unless you have a group on the ring that's ortho or para that the minus can do resonance in and end up on a heteroatom. Okay? Same thing here. You can only do this if the charge ends up on a heteroatom. It doesn't end up on a heteroatom. Right there. You see it in the resonance structure. The major resonance structure. Can a nucleophile add to just a plain double bond? Well, if it did, you would get this anion after it came in electrons here. Is that on a heteroatom? Can you do resonance and put it on a heteroatom? Then you ain't doing that reaction. The reason you can add to this double bond is because ultimately because it's conjugated with the carbonyl, this allows this to happen. That's why it's also called sometimes a conjugate addition. But some chemist named Michael really did a lot of this, and it's called a Michael addition. Okay, at this point, what type of nucleophiles can do this? Well, what type of nucleophiles have we seen? What about a Grignard? Is that a good nucleophile? Certainly. Grignards can do this. The thing you have to consider is which is preferred? How would a Grignard react? Would a Grignard react 1,2 or would it react 1,4? Now this could be an in-depth discussion. We don't have a lot of time. There's some other things here about kinetic product versus thermodynamic product. Basically what it says is, well, to give you a summary. If the nucleophile can serve as a leaving group, you'll typically get a Michael addition as your product. If it can't serve as a leaving group, you'll typically get the 1,2 addition product. That's not a big thing, I don't think, at this point. With the limited time we have. Okay, let's do some examples. And I'll talk about what I just said. Here we go. We got this. First, Grignard, or like methyl lithium. This is essentially methyl anion. Grignards prefer 1,2 products. 1,2 is basically a direct addition, electrons up, and we can get that's 2 methyls. I'm going to draw the new one in like that. This added electrons up. That's going to be minus What's the purpose of the H plus workup? Just to put the H on, okay? And so you end up with that tertiary alcohol. All we did was add nucleophile carbonyl and then protonate the oxygen. Everybody see that? That's a direct 1,2 addition. We did that a month ago. Now, alternatively, cuprates, remember cuprates? We used them when we acted acid chlorides with cuprates to make ketones. Cuprates give the 1,4 product. Show the 1,4 product of this reaction. The Michael addition product. This is also a methyl minus source, but it's different, and indeed, it's really the magic of copper here. I can't tell you any more than that. The product is going to look like that there. Any questions about that? Those that did not get it right, why not ask a question? What'd you get?
I had accidentally put 2 methods.
Why'd you put 2 methods?
I thought I made 2.
Just like when we reacted acid chlorides with cuprates. Other questions?
How often would it make an OH instead of getting a double bond alkene instead of carbon?
Mechanism. This adds here, electrons here, right? We said that it's going to do a Michael addition.
Right.
There's your Michael addition, phenyl. So the methyl just added, made that bond, anion here.
Right. But couldn't it jump up to the oxygen then, since we're doing a 2-step process?
You mean resonance?
Yeah. How often would that happen?
What do you mean? What?
This result, and then adding the H on
Well,
point.
Resonance is always there, right?
Right.
Resonance is always there. Whenever this added, we got a pink intermediate. It wasn't white, it wasn't red, it was pink. Sometimes we only show the red structure, but we have to remember it's pink. Resonance is always there. So what's the question from there?
What percentage of the result after the H plus workup will be make an alcohol group there?
Okay, if you make this, what is this product called here? Enol.
True.
Okay, and this is called the ketone. Okay, so the question you were asking is, what's the percentage of enol versus ketone? Well, I would refer back to page 1. Keto versus enol forms. The keto form is highly favored, except for certain cases where it's not. Is there a reason why it would not be, this would not be the favorite form? I don't really see a reason. This double bond is not conjugated with anything. There's no hydrogen bonding potential. In this mechanism, could this first become protonated when we throw in the H plus step? H plus workup? Sure it could. But this is an enol. And enols are in equilibrium with this, and which side's favored? That. What's the mechanism going from here to there? We did that. Yes. This is a difficult question that comes up. Glad you asked it. It gives us a chance to review the enol-keto tautomerization in equilibrium, which is favored. Okay? Yeah. But ketone's favored. That's why I drew the ketone here. But good questions allow us to discuss things. There was a question over here.
No, that was not one of the questions.
Okay. Miscellaneous, interesting. If you make Grignard and do a reaction, you get the 1,2 addition product. You also get minor traces of the 1,4 product. But it's been shown if you use super grain 100% magnesium, you only get the 1,2 product. See, that's 1,2, that's 1,2. This is actually 1,4. The reason you get some 1,4 product there with the Grignard is because if you use low-grade magnesium, it has some what impurity in it. It has copper impurities in it, and copper will lead to some of the 1,4. Okay? Magic of copper. Copper makes things go 1,4. Can't explain why. So this is just an interesting experiment that was done. If you use super-grade magnesium that has no copper in it, you'll only get the 1,2. Grignards add 1,2. What other nucleophiles can add? Amines. Heteroatoms typically prefer 1,4. Because see, a heteroatom can turn around and be a leaving group. And I said if it can be a leaving group, it'll do 1,4. So the question is basically, what's the 1,4 product look like? Well, it looks like that right there because this added here, electrons here, we get ring, nitrogen with 2 H's, and the methyl, that's a plus charge, that's a minus. We can show resonance structure if you want. And then how do you get this product? It's just a proton transfer. The H plus moves from the nitrogen to here. See, there's 1 H. There's 1 H. But now there's how many there? Now there's 2. Basically here we don't have to supply an H plus for workup because the H plus comes from the nucleophile. That's just a good old Michael addition of an amine, proton transfer, and there's your product. Down below, here's just a Michael addition of a ethoxide. Oxide adds, you get anion. Where does anion get an H from? From ethanol. So the alcohol can serve as the proton source. Now what are we accomplishing here? We essentially are getting nucleophiles on the beta carbon relative to the carbonyl. This is what we're able to do. So in terms of synthesis, if you're asked to synthesize something, and you see some kind of substituent beta to a carbonyl, how can we get that substituent there? It says synthesize these from cyclohexanone. draw that. What are we trying to accomplish here? How can we take this and get a phenyl group here? I mean, there's no reactivity here right now. There's no leaving group. There's nothing. How are we going to do a phenyl? You want to go backwards? Reactive phenyl cuprate with what? The alkene, yeah. And so if we have this, we can react this with phenyl to copper lithium. Phenyl cuprate, yeah? Cyclohexanone, work our way back to it. Aha! Now we're going to make this from that. Now we could do an aldol, but aldol would be breaking this open into something like, you know, this. Or we're not asked to do that. We're asked to come from here, so we can't break open the ring. Remember, we did this. I referred to it today. How can we put the double bond in here?
Cl2KOH.
We can go back to maybe a bromine here. If you had bromine here, how would you make the alkene? E2. Sterically hindered base, E2. And so how do you put the bromine there? Well, it's just a bromination. What else do you want to use other than bromine? Acid or base? Base gives exhaustive bromination. We don't want exhaustive, we just want one. We want to use acid catalyst, HBr, acetic acid. And the reacting species would be the enol. Enol reacts with bromine. We actually don't have to use HBr because we talked about how this reaction is autocatalytic. Okay, but see, this we talked about already, including 2 weeks ago. The new thing is, when you see something with a nucleophile beta, you say, aha, this came from the amine attacking there. How about this guy? How would you make it? This, instead of reacting, what do you want to react that with to get this? What happened there? Instead of a nucleophile adding Michael addition, it looks like a nucleophile added to carbonyl. What was the nucleophile? Methyl magnesium iodide. Those Grignards add to carbonyls directly, 1, 2. Cuprates do what? Michael addition. Many things do Michael. Actually, an enolate does a Michael. Can an enolate? Yeah. Okay, let's try to, there's some sort of miscellaneous things that you can look over. It's basically nothing new. It's just some applications of what we did. We're about out of time. You can use it sort of just to think more about conjugate additions. Super glue. You see this here. What is that, Durabond or something? Durabond. The last thing we'll show on the white handout. Tylenol is toxic. Toxicity of about 100 milligrams per kilogram. Why? Your body oxidizes Tylenol to this species here. But then what do we have right here? Alpha, beta, unsaturated carbonyl. These things tend to be pretty reactive. And in the body, your proteins will start doing Michael addition. Okay? Well, that screws up your proteins. Proteins in your eyes or in your liver. Lots of proteins in the liver, and it causes toxicity. It's a toxic metabolite with a conjugate addition, Michael addition acting. The other thing I wanted to show you, because it goes with that Dermabond, is there super glue? Oh, very back, super glue. Chemistry of super glue. There's super glue. It's an alpha beta unsaturated carbonyl. It will polymerize on exposure to base. Go from a liquid to a polymer. Okay? There's base everywhere. There's base right here on this desk. All it takes is a tracer mount. There's base all over your fingers. You squirt some on your fingers, what happens? Turns to hard glue. Okay? How does it happen? Michael addition. Give this anion. But what happens next? This anion can do another Michael addition. Basically, it's Michael addition after Michael addition, and it polymerizes. Starts with a Michael addition, though. Okay. Sorry we're rushing at the end. I wish we could have made the test, but we could not. Standard format, nomenclature, such. There will be a comprehensive spec problem, such as in the workbook. Chemical test, we did haloform, DNP. What else did we do? Haloform, iodoform, 2,4-DNP. I think that was it. But we also have the tolerance and whatnot. Questions? Take off if you need to, guys. Test on Friday. Questions? What? Synthesis? There probably will not be multi-step synthesis like on test 1 and 2. There may be multi-step line reactions, but it won't be kind of the retrosynthesis.